Those are our lessons from chapter 17. Beyond that, it's a bunch of nomenclature stuff that you just have to look at the rules for. Okay? So, a little bit of foreshadowing. Benzene, incredibly stable, low energy. What would we expect the chemistry to be for this molecule? What was that? Somebody mumbled something.
High energy and not stable.
It's high energy and not stable. What would I expect it to do? What reaction? So this structure is incredibly high in energy because it's not aromatic for a couple reasons. One, we don't have the proper pi electrons, and this carbon is what hybridization? sp3. It can't even push pi electrons through it because it didn't have a p orbital. Okay, this compound will take the electrons in that carbon-hydrogen bond, and it will share them with the positive charge. The result being that the hydrogen has lost electrons and comes off as H+. What happens with the rest of the structure? What's special about this guy? It has an aromatic ring. We'll address the leaving group. Well, we won't address the leaving group ability. That bromine is not the greatest leaving group because it would form a positive charge on that ring, which is not very stable. So if you think back to the substitution reactions from first semester, if we were to try and react this under, say, SN1 or even SN2 conditions with either, let's just pick a good nucleophile, cyanide, okay, it's not going to do the substitution. We don't expect that to work. At the very end of our aromatic structure or aromatic reactions, we will talk about a mechanism where we can get the halogen to leave, but it's very particular conditions to force that to happen. Okay? So, there was a request in the last time I taught this class to start the lectures off with reactions, with all of the possible reactions. Somebody really wanted to see everything before I started talking about all the details. So, this is everything. I have no idea why anybody would ever want to see everything at first, because I look at that and freak out. Okay. But this is everything that you are responsible for coming out of chapter 18 and a little bit more. The birch red for reduction, NAS, and the elimination addition reactions, those I still have to write up a handout for, and I'll get that typed up sometime over the weekend, so hopefully you'll have access to that to read over it and get a little bit more background and not listen to me talk about it. Okay? So our primary section for this chapter is really focused, at least chapter 18, is in the subject known as the EAS reaction. Okay? And our EAS is superimposed over our aromatic ring. So what we're concerned about is all of the possible reagents that we can use to get some functionality onto our aromatic ring. Once it's on there, we can start to look at different aspects. What can we do with it once those functional groups are attached? The other thing that we're going to have to address is what if we start with something other than just straight normal benzene? So if you look to the far right, I've added an X to the top of that, which is now in the shadows. But eventually you could see that. Okay? That X now changes the structure of our benzene. Okay? If we had just benzene, all of the hydrogens are the same, so it doesn't matter what hydrogen we exchange out. As soon as we put an X group on it, are those hydrogens now all the same? No, which now we have to worry about how is that going to affect where we do a substitution, what hydrogen ends up getting exchanged. That's going to be dependent on this idea of activators and deactivators and what things classify for those. Okay, and all of the terms that go along with it. Okay? For your opinion's sake, do you guys prefer to see a big, massive summary slide to start each of these things, or would you prefer to see that at the end? I can show it in both places. You want to see it right away? Okay, so we'll put it all up. I'll try and include it for every single functional group we go through and look at the reactions. I'll try to get them all condensed onto one slide for that particular functional group as best I can. This is probably one of the neatest looking versions of this type of slide that I've seen. Okay, so realize that it can get very, very messy. So I'm going to refer to this slide as the initial slide. So later on in the lecture, we'll hear about initial slide. Let's address what's happening with electrophilic aromatic substitution. Okay? So which part of that name of the reaction do you want to look at first? Electrophilic, aromatic, or substitution? Okay, aromatic, I agree. I like that one too. Aromatic does classify to all aromatic structures. Anything from 17 that was classified as an aromatic compound will follow similar chemistry as this. However, that's a lot of different things to look at. Primarily, we're going to be focused on which compound? Benzene. So let's just start with a nice benzene structure. What's the next thing we want to address? I know that doesn't show up very nicely, but it's a benzene ring, right in the middle. Electrophilic or aromatic? No volunteers, you're getting electrophilic. So let's look at electrophilic. What does electrophilic mean? What? Electron loving. So that would be a structure that has what charge associated with it? Positive charge. Let's take a look at our aromatic ring. Would we expect our aromatic ring to act as an electrophile? Why not? It's stable, but that doesn't quite address the electron balance.
Resonance?
To do resonance, what do we need?
Electrons.
Electrons. There's a ton of electrons in that pi system. Okay? So our aromatic ring is not very likely to act as an electrophile, which means if we're going to break this name down, we're going to have to introduce an electrophile. So what's a good symbol for an electrophile? Thank you. I had one class give me a heart. Like, this is ridiculous. I can't draw a heart. Okay. Let's go through and do another symbol to this. What else can we add to that electrophile so we can address something about its chemistry? Because it's just E, we don't know what that means. We want to make it a positive sign because it's electron loving. To be electron loving, it needs to be positive, so it can accept those electrons. You know, it's a little bit odd, but that's the way it works. Okay, last part of this name of this reaction was substitution, which implies that we are doing a reaction. So we can bring in our arrow, and it means a substitution reaction. So that E needs to substitute for something in our benzene ring. Well, what somethings are possible within our benzene ring? Hydrogen and carbon. Which do we do the substitution for? Why hydrogen? If we were going to do a substitution to get our carbon out, we'd have to break 4 bonds, slide the carbon in, or slide our electrophile in where the carbon was, okay, and then reform all of those bonds. Okay? That's a lot of bonds to go through and break, particularly when we're looking at something that is theoretically supposed to be simple, the basics of organic chemistry. So what we're going to do the substitution for is a hydrogen. And we can put on our, what do I call it, blue electrophile on, and we'd be left with hydrogen floating off as what charge? Why should it be positive? Two big reasons. It's replacing the electrophile. The electrophile came in as a positive, so what should the hydrogen be leaving as? Positive. We got to do that one-for-one swap out. Okay, so this is the basics of our EAS reaction. We have some electrophile, we have our nucleophile, which is our benzene ring, and we do a substitution reaction where the hydrogen is replaced on the benzene ring with an electrophile. Right, so we could go back one step, and if we look at our reaction in each of those cases, all of those red atoms under our EAS are our electrophiles. Right, and somehow or another we have to generate those electrophiles so that they can do the substitution with the ring. Okay? As with most reactions, once we've got an idea of what's happening, we'll also have to look at a mechanism. Okay? What does the electrophile need? Electrons. So our benzene ring is going to have to supply electrons. Where are the electrons going to come from? a pi bond within our within our aromatic ring. So we can show the mechanism with the electrons coming out from the ring and hitting up with that electrophile. Okay, we end up generating that first structure as an intermediate. So a couple things that we now want to consider. Number one, is that a good thing to do? Is that a simple step? Or is that a really hard step? Nice sound effects.
I would think it would be hard.
Why hard? I agree. I think it's a very difficult step.
Isn't it hard to pull those like much more better?
Why?
It's pretty stable.
The ring started incredibly stable. To pull the electrons out of the ring, we have destroyed aromaticity. That is extremely bad. Okay? So that's not a good situation. And we've destroyed it in multiple ways. One, we've pulled the electrons out, but we've also introduced that carbon, which we said was what hybridization earlier? sp3. I can't even push electrons through that carbon. So it's not even just removing electrons. I now prevent the path of electrons throughout the structure. Isaac.
Why are we going to push electrons around the ring so much if the hydrogen is on the carbon?
That's going to be the next question. We're first okay with this first step. Okay, so number one, very bad thing to do. Okay, we'd say, okay, why on earth would we ever do this step? Okay, so we would generate this carbocation and we say, okay, something's wrong with this. We're going to have to fix this somehow. With a standard alkene reaction, how do we fix the positive charge? With electrons coming from, with a standard alkene reaction. So we're looking at an alkene addition reaction. The addition happens the same in both EAS and a standard addition reaction. It's a secondary nucleophile comes in. So if we reacted HBr with an alkene, the alkene picks up a hydrogen, leaving a carbocation. The bromide nucleophile comes in and stabilizes that positive charge. We don't see that in the case of the EAS reaction, because what would that further do to our structure? If we put, say, a bromide on that carbocation, that carbon now becomes sp3 hybridized as well. So we even further shut down the ability to move electrons through it. Okay? So we aren't going to bring in a nucleophile. So now what we've got to do is say, okay, is there a way to stabilize the positive charge? Because right now, when we just look at that first reaction, we're saying that is an incredibly unfavored reaction. I do not want to do that. Okay? So something has to somehow contribute to allowing that reaction to occur. What's something that could potentially lower the activation barrier for that reaction? Make it more likely to occur. Resonance. Okay? So now that we've generated the carbocation, we look within our structure and say, is there some way that I can stabilize the positive charge? Well, we look at the pi bonds. And we can move the pi bonds progressively around the ring. You'll notice the positive charge starts to shift all the way around the ring. When we're looking at our EAS reactions, these are the three resonance structures that I would expect you to draw and come up with each and every single time. Okay? Each and every single time. So if asked to provide a mechanism, if you go from starting material to this first structure and then jump straight to your product, you lose points because you didn't provide all the resonance contributors. Okay, so if you think all the way back, at least people that have had me when we did Lewis structures, and I said if it's possible to draw more than one structure for an individual formula, okay, more than one resonance structure, how many answers do you have to provide? Every single one that contributes to the resonance structure. So that means when we're going through the mechanism, we have to specify every single resonance contributor. There is no shortcut. Okay? This helps in, say, chapter 16 when you're looking at reacting an alkene with HBr. If you draw out all of the intermediates and the resonance contributors, you can see how to make each of the products that sapling may be suggesting you to find. Okay? So drawing those structures out can help you. These structures, because they are the main contributor to why the EAS reaction works, we've dropped the overall energy of that first intermediate because we've stabilized it through resonance. These structures pick up a special name. They get the name called sigma complex. Okay, why might we call it the sigma complex or sigma complexes? Let's go back to that carbon again. Said the hybridization of that carbon was what? What are the types of bonds that that carbon has? Anything else? No, just sigma bonds. These are sigma complexes because we've taken our aromatic ring and we've introduced a carbon that only has sigma bonds. There's our name for the sigma complexes. Okay? So we've got all of these resonance contributors to stabilize that intermediate, which then brings up the very last question. These are still ridiculously unstable. Okay? We need to permanently stabilize that positive charge. And there are two ways in which to do it. Okay? What are those two ways? One of which is actually shown up there. We can take the electrons away from the hydrogen. So if we go to that last structure, we can take the electrons away from the hydrogen and form our pi bond. Ta-da! There's our aromatic compound. Fantastic. We've restored aromaticity and we've done the substitution. What's the other way?
Isn't it taking electrons from the pi bond?
No, that puts us in all of our resonance situation. The big hint.
Go back.
How do we go back to where we started? Take the electrons back from the electrophile to take us back the other direction. So that first step of the reaction is in equilibrium. The last step, not so much. Okay, so for this reaction to really work, our electrophile has to be more unstable than H+. Okay, so that way we can push to just forming our substitution reaction. All of these resonance structures you will be drawing again and again and again. Okay, so please get used to drawing them out. If you haven't drawn them out already, I would say start drawing them now, but I'm going to move on to the next slide. Okay. Oops, I don't want to quite move on to the next slide. We move into lab. What's our number one goal in getting, once we move into lab? Leave lab. Which means for us to leave lab faster, what has to happen with our reactions? Our reaction needs to go as fast as freaking possible so it can be done with its chemistry and then we can finish it and leave. All right, that is our goal. And you may all laugh like, ha ha ha, real chemists don't do that. No, real chemists don't want to be in the lab either. They try and get their reactions done as quickly as possible as well. Okay? So how can we speed the reaction? This works with all reactions. I heard catalyst. We'll address the catalyst in just a second, but that's too specific for me. So we could increase the energy by adding heat. Problem with adding heat, it activates all reactions, which could be a bit dicey because we could have a bunch of side reactions that are possible as well, and we don't want those side reactions to go. So we've got our electrophile and our nucleophile, right? What happens if I make the electrophile less positive? It's going to get slower. Why? For the reaction to work, I need to have an electrophile. It needs to be positive. If I make it less positive, less likely to react. So how could I speed the reaction? Make it more positive. So make our electrophile as positive as bloody possible. That's going to make it react faster. What's the other option? Let's make the nucleophile more negative. Those are the two things that we'll end up addressing. Okay? Comes back to the same basics of the reaction. Make our electrophile more positive, our nucleophile more negative, and everything goes faster. Okay? Let's take a look at the electrophile first, because that's a little bit more more easy to work with. Okay, so here's some example electrophiles that we will see in this chapter. Which of those is the most electrophilic? So think about it a little bit. I know some of you aren't next to other people. I'll give you another 30 seconds. Go ahead and share your answer with someone around you. See what you think. We can call it 1, 2, and 3. Structure 1, structure 2, structure 3. Which one's the most electrophilic? Okay, hearing some answers float out here. The one that is most electrophilic is number 2. Why would number 2 be the most electrophilic?
Positive charge.
2 oxygens are, yes, going to draw electron density away, but it is formally positive. Okay? Our electrophile should be as positive as possible. The middle one, number 2, starts positive. That's an exceptionally good electrophile. Okay, let's make it harder. What's the next one?
Number 3.
Why would 3 be the next one? We've got 2 electron withdrawing groups. Both the oxygen and the chlorine will withdraw electron density away from the carbon, okay, through what's known as an inductive effect, right? I would argue that we've got an extra thing going forward on that one, because I can make that same argument with the first one. Bromine's electronegative. Can it draw electron density away? Why not? They're both electronegative, so the net pole is nothing. So we don't get an electronegativity argument there. So let's go back to our third structure. What's the other contributor to this, being that carbon being positive? We could say that, but that's going to push again, I think, with the inductive effect. 9-letter word. We have a resonance structure to take the pi electrons and dump them up on the oxygen, which pulls the electrons away from our carbon, and we'd end up with a structure where the carbon is formally positive. Okay? So that last one does work out for us as being a pretty electrophilic carbon. And then we still have our bromine being the least electronegative, the least electrophilic. Okay? So by looking at this, we can kind of go through and evaluate which of these is our best electrophile, which of these is our weakest, and kind of play around with that. So now what I want you to do is just focus on the bromine. Okay? How can we make the bromine a better electrophile? And to facilitate that a little bit, I want to make this bromine a better electrophile. What charge does it need to become? Positive. I lied. I don't want to make that bromine positive. You'll see why in a second. I want to make that one positive. Told you, you'll see why in a second. Give me a break. Okay. How can I make that bromine positive? I want to somehow get the other bromine to take the electrons. Okay, but that bromine's not going to take electrons right now because the electronegativities are the same. So what I want to do is introduce some other species to come in, and just for the sake of argument, I'm going to call that species Fe. And this species Fe is going to want to take the electrons or coordinate to one of those bromines, which would mean, we'll get to that, that bromine that's not boxed in becomes what charge? It's going to become positive. It actually lost electrons in that bond. Does it want to be positive? No. So what does it do? It pulls the electrons out of that bond, and we end up with our purple boxed oxygen bromine being our positive. There's our electrophile. Okay, so now for the sake of argument, what was this Fe thing that I decided to bring in? It's iron. a nice little catalyst. This iron is not just iron metal. It's actually going to be iron tribromide. What charge would the metal take in that complex? Doesn't even really matter. What charge does any metal really take when it takes a charge? Positive. What could we do with a positive charge? Give it electrons. The iron tribromide will accept electrons from our bromine, polarizing the Br2 bond, generating our electrophile. What does the iron tribromide act as in this case? A catalyst. Okay, let's get more specific with it. What type of catalyst is it? What did it do in this reaction? So if we drew out the product of this, end up with our iron, now with 4 bromines and Br+. What was the role of iron tribromide? Sort of. Electron withdrawing would mean just that it polarized that bond. But if we look at the product, is it just electron withdrawing? No, it actually changed the bonding structure. So it's a step above electron withdrawing. What's the step above? What type of acceptor? I agree. An electron acceptor. Is there a name given to species that are electron acceptors? Lewis acids. The iron tribromide will act as a Lewis acid. So when we're trying to go through and speed any of our electrophile reagents, in a lot of cases what we end up doing is adding an acid of some sort to help us generate the electrophile. In most cases, it's a Lewis acid that we're adding, because what that will do is polarize our electrophile, allowing it to be more electrophilic.
So you can't call it just an electrophile.
You'd call it a Lewis acid. You could classify it as an electrophile as well, because it's accepting electrons from something other than hydrogen, or it's something other than hydrogen that is accepting electrons. The standard terminology for it is a Lewis acid catalyst. Okay. Questions? Now we enter it all. Let's go ahead and do some problems. Highlight. We're not going to do problems. So we can start with our first list of our reagents, okay, our electrophiles. I just looked at the bromine-bromine reaction. What would we expect of a chlorine reaction? Pretty much the same thing. So we can substitute bromine or chlorine for a hydrogen on our aromatic ring by using a Lewis acid catalyst. The iron tribromide is typically what's used when we're using our bromine. We could throw in an iron trichloride for chlorine. But there's another reagent that we could have thrown in there. Those of you that have read ahead. Aluminum trichloride. Why would aluminum trichloride do the same thing? So number one, aluminum is what kind of a species or element? It's a metal, so it's probably already picking up a positive charge. It's a little bit better than the iron for a separate reason. What is the hybridization of that aluminum?
SP2.
sp2, which means what is left over?
P.
An empty p orbital. Huh, where have we seen that before? Hint, the answer is, that's a valid answer. Boron. Our boron reagents do the exact same thing with the empty p orbital. Huh, where's boron relative to aluminum? Oh, right underneath each other. Look at that. Periodic table awesomeness. Okay? So aluminum trichloride can also be tossed in there to generate your electrophile. What I've gone through with each of these reagents is highlighted our electrophile in red, as well as put it with that positive charge so we can see it stand out a little bit better. We got a couple other reagents that we can go through and do with our Lewis acids. We can generate carbon nucleophiles. So just straight up R positive, and we can also generate this other one at the bottom, okay, which has a fun, goofy name. How can I get a positive carbon? Take a look at the first one. How could I possibly get a positive carbon? What was that? So we should probably, we don't know anything about a pi orbital because it's just R. Bond, so something needs to be able to take the electrons away from that R. What atom should we attach to that R? Something very electronegative. Oxygen's very electronegative. Why would we not attach oxygen? How many bonds does oxygen need? 2. Typically we add in the OH. What's the problem with that? We have another source of reactivity. We want to avoid that as much as possible. So we want to put in something in place of the oxygen that only has what bond? Or one bond, which means halogens. The standard halogen that we use for this reaction is chlorine. Okay? But I want to make that carbon really positive. Is there something else I could potentially add to this to get that chlorine to say Fu carbon and take the electrons? Hydrogen there? That's not going to happen, right? Hint, we just talked about it. We need something with an empty p orbital that could accept those electrons.
Some sort of iron catalyst.
Switch it up, get less specific with that. We can go with our Lewis acid catalyst. Our aluminum trichloride will work really well. Okay, so we can use AlCl3. Okay, we get effectively the same result that we got with our chlorine. Okay. Next one down. Okay, I particularly like that one. I think it's a bit silly. I'll address that in just a second. Which is our electrophilic atom in RCO positive? I actually already told you the answer just a few seconds ago. R, carbon, or oxygen? Carbon, and I like that answer. Just a few seconds ago I said I highlighted all of the individual electrophiles as red. Our carbon is the electrophile. That's a bit odd. Why is the carbon the electrophile? It's not positively charged. Okay, why is the oxygen not an electrophile? It has a positive charge. Aren't things that are positive supposed to act as electrophiles? What does an electrophile need to do? What's the definition of our electrophile? Accept electrons, and then we have to take it a little bit further. I know I've left this part of it out. From another species. How many electrons are currently around that oxygen? 8. Can it accept more electrons? No. This is the official Lewis structure for this compound, but it's not the one that shows us the chemistry. To see the chemistry, we need to look at the best worst Lewis structure. Just a sec. Oxygen does not want to be positive, so what does it do? Take electrons from within the structure, because we can't accept electrons from outside. Where's the closest source of electrons? Pi bond. What's the result? Our carbon now becomes positively charged. Between these two structures, which one is the best one? Again, I just gave you the answer on this. I said the top structure is our best one. I do really honestly like and appreciate that you say the bottom one is the best answer. It is technically wrong, though. Why is the bottom one not the correct Lewis structure? This goes all the way back to first semester in the bloody nuances of drawing Lewis structures. I think I heard somebody say it has nothing to do with the charge, it has to do with octets. For it to be a valid Lewis structure, the octets must be satisfied. Does carbon have its octet satisfied in the bottom structure? No, it only has 6 electrons, so it is technically not a good Lewis structure. The one above it is the best Lewis structure because all of the octets are satisfied. Why did you guys like the bottom one better? I agree with you. I like the bottom one a lot better. I've put the positive charge and I take it a step further than in the center. I can see where you're going with that. There's something I think a little bit better than that. No? Why is it more stable? So that more stable goes back to, we could even bring in symmetry with it. I'd say there's an even easier option. Which atom would rather have the electrons? Carbon or oxygen? Oxygen. Which atom would hold a positive charge better? Carbon or oxygen? Carbon. That's why that one looks good to us. Okay. Technically, not a good Lewis structure. So it is the best, worst Lewis structure because it's an invalid Lewis structure, but it's the best of the bad ones. Okay. Name for this ion? Yeah, there it is. It's the acylium ion. Remember how I said a little bit earlier? It's my favorite compound because it's kind of silly. I will be here all week. So we can start all the way back with our carbonyl compound and a chlorine leaving group. The chlorine is such a good leaving group that it can be withdrawn from the structure. When it leaves the structure, we form that best, worst Lewis structure that then is formally stabilized by the official Lewis structure, and we end up with our electrophile. You'll notice to help facilitate the removal of that chlorine, we have again added that Lewis acid catalyst with the aluminum trichloride. Okay, so again, the chlorine will share its electrons with the aluminum, but now it's got too many bonds, so it takes the electrons away from the carbon, and we end up with our acylium ion and our aluminum tetrachloride side product, intermediate. Okay? Questions? How would these react with a benzene ring? Well, make them, and then, come on, step back, keep going. And instead of it being an E, you make that E a Cl, or the acylium ion. You could make it be your carbon with the double bond oxygen in our R group, so that when we go to our product, what do we end up having? Our carbon with our double bond oxygen in our R group. What if we did the second one on our list, where it was just an R positive? Well, we go through the exact same mechanism, except everywhere there's E, we have R. Okay, so the mechanism will still hold true all the way through these, okay, as long as we deal with benzene. Okay. Those last two, we end up with positive carbons, and we're making carbon-carbon bonds. Carbon-carbon bonds tend to be fairly rare, a little bit more difficult to make. So when we can make a carbon-carbon bond, we usually get pretty excited about it, and whoever discovered it gets to attach their name to it. So those last two are associated with, pretty sure it's misters in both cases, Friedel and Crafts. So those last two reactions are named after those two scientists that came up with the correct reagent combinations to generate those electrophiles. Okay. We can take it a step further. I don't know if I did. Nope, I didn't quite. Take a step back there. We could look at the names given to each of these. If we use chlorine or bromine, what we end up looking at is some kind of halogenation for our substitution. If it's an R group, we're looking at an alkylation. The full name given to it would be a Friedel-Crafts alkylation. For the last one, Friedel-Crafts acylation, because we have attached an acyl group. This is what is an acyl group. Okay. As we start to get further into looking at the alkylations and acylation reactions, some issues pop up with them. Okay, and we'll talk about those again in a little more detail. But for the alkylations, it requires an active nucleophile. I haven't told you what active means yet, okay? But that's going to become important. To do the Friedel-Crafts alkylation, the nucleophile must be activated, must be really raring to go. Any ideas why it must be raring to go? Positive carbon. Is that stabilized by anything? Or R positive here? Let's go through and actually pick in an example. That was my electrophile. Is that a particularly stable structure? We have a technically methyl cation, extremely unstable, not very likely to form. Okay, which means even if we add the catalyst, it's not going to break that bond very easily, which means the nucleophile has to be extra strong to come in and force that whole cleavage and force the reaction to occur. When we move to the acylation reaction, we don't have to stress about that. It'll work with pretty much all rings, okay, or all nucleophiles. Why? Because our acylium ion was resonance stabilized. Okay, that resonance stabilization allows for its formation a little bit quicker and easier, so it can work with any nucleophile that we could possibly look at, either activated or deactivated. Okay. Sorry, questions on looking at your electrophiles with the Lewis acids? Okay. Just as we kind of suggest when we're looking at all of our catalysts, in all cases what we end up doing is adding some kind of acid, be it a Lewis acid or a Bronsted-Lowry acid. To generate this electrophile, one of my favorites personally, okay, which you will undoubtedly see on the test, okay, to make this, we have to react it with a strong acid, or we have to make it from a series of strong acids. We're going to take HNO3, H2SO4, and react them with each other. The next sequence of steps will end up generating the nitronium ion. Okay? Why might this one be a fascinating reaction to me? Think back to Gen Chem. If you were asked to define what H2SO4 is, what would you say? Strong acid, good. HNO3? Also a strong acid. So with that information in mind, let's go to our reaction. This is how this reaction works, by the way, so I'm not just making things up. What has to happen mechanistically in that very first step? What changes happen to HNO3? It accepts a hydrogen, right? Where did that hydrogen come from? The H2SO4. The oxygen on our HNO3 attacks the hydrogen on our H2SO4 to form our intermediates. What did the H2SO4 act as in this reaction? Okay, what's the definition of a nucleophile? An electron donor, where it's donating the electrons to any atom that is not a hydrogen. Okay. What actually occurred in this reaction? What did we exchange as we went from reactants to products? A hydrogen. So nucleophile, electrophile is bad definition. It's a Bronsted-Lowry situation. Our H2SO4 did what? It donated the proton, which meant it's a Bronsted-Lowry acid. What did the HNO3 do? It accepted, which means it is Bronsted-Lowry base. So mechanistically, that all makes sense. Now we open up that Gen Chem question again. What is HNO3 defined as? A strong acid. What do strong acids do? Donate hydrogen. What did HNO3 do in this reaction? accepted hydrogen. It acts as the complete opposite of what you were told to memorize in general chemistry. Love it when that happens. Okay? Why does it accept the hydrogen from the H2SO4? No, because there's still technically an OH group on the H2SO4 as well. H2SO4 is a strong acid than HNO3. Just because it's a strong acid doesn't mean it can't act as a base. We can throw in a stronger acid at it, and then we can force it to act as a base. Okay, so even though both of these species are ridiculously strong acids, H2SO4 is the stronger acid, and it will force this reaction to occur. Once we form that intermediate, you'll notice that we have a really awesome what in the blue? This section right here. It looks like water. Water's acting as a really good leaving group. Mechanistically, what happens? It takes the electrons away from the NO2. We have H2O as our leaving group, and we're left with the positively charged nitronium ion. Kind of a fascinating reaction. Okay, unfortunately, we won't do this reaction in lab. Sorry. Okay. It was one that I wanted to do, but it involves fuming nitric acid, and that's also a little more dangerous. So kind of backed off of that. And it didn't work. So. Okay, questions about the nitronium formation? Next one, we can put on, I'm not even sure what to call this one, sulfonium ion. How could we possibly make this one? SO3H looks an awful lot like maybe if we took we had those take the electrons. Isn't that SO3H right there? How could we get the OH to take the electrons away from that structure? The OH would need to be made into a good leaving group, which would mean water. It needs a hydrogen first. Where can we get that hydrogen from? A strong acid. What do we end up doing? We take sulfuric acid and we effectively react it with itself. If there's a lot of water present, we minimize the reaction, looking at Le Chatelier's principle. Okay? So we put in concentrated sulfuric acid and we heat the crap out of it to help facilitate and get that electrophile to form. Once the electrophile forms, it can react with the ring, and now we're set where it's attached to the ring. We don't have to stress as much about it. Okay? This particular reagent doesn't get used all that often, so it's not a huge one to remember. But if you go back and look at that summary slide where we showed this reaction, you'll notice that I didn't give you just a single arrow. What I gave you wasn't an equilibrium arrow. The sulfonation reaction is reversible. Okay, so I can put on the sulfur or the SO3H group, and I can take it off with similar conditions. Being able to put something on and take something off is a pretty key characteristic. So it does show up in a few cases, and it is the only one of these reagents that will allow us to do that. Last one. What's the electrophile here? What atom? Carbon. Good. It's our central carbon. How can we make this positive carbon? Yes, there are a couple answers here. You should be able to give me an answer because the last slide had it on it. Yes, aluminum trichloride reacting with. Yeah, we got our carbon. It's going to have those pieces. What else needs to be attached to it? Chlorine. We could do a Friedel-Crafts alkylation with this one. We could generate it in that case, but that uses what type of catalyst? the aluminum trichloride, which was a Lewis acid catalyst. This slide is about Bronsted-Lowry acid catalyst. So how can I make that carbocation without using a Lewis acid? Okay. Good. We are somehow adding H+. Cl is a bad option. Why would adding the Cl be a problem? Also acts as a nucleophile, cancel out our electrophile. So the acid that we'd be adding would be a strong acid that's non-nucleophilic, H2SO4, good option. What do we start with? Where would the hydrogen add to that structure to get the positive charge in the middle? We don't want to use an alcohol because that introduces all sorts of other issues. We want to simplify our chemistry as much as possible. Not a bad idea. We could try and do the alcohol, but that, again, you bring in water and other functionalities. We want to minimize that as much as possible.
You really want to add like a water.
Okay. Basic skeleton has to be there, so let's leave that positive charge. Could the hydrogen have added to the middle carbon? No, why not? Okay, starting to get down to the right path when you're dealing with substitution patterns. If the hydrogen was added to the middle carbon, we would see a hydrogen added here, right? How many bonds would that carbon have? 4 bonds. Can it be positively charged? No. So the hydrogen very clearly was not added to that center carbon. So where was the hydrogen added then? It's a hint, there's only 3 other options and they're all the same. To one of the carbons. Okay, so we had a hydrogen out on one of those positions. So let's remove one of those hydrogens. What charge would that carbon be? Because we're going backwards now.
Negative.
Has to be negative. Why negative? Because we added, we took away hydrogen H+. So that's a negative. What functional group did we start with? There it is, an alkene. Okay, so we can start with an alkene, react it with a strong acid to generate our electrophile, and then throw in our benzene structure to react. Also a less common one, but it does show up occasionally. Okay, questions? Names attributed to these. Come on. Nitration, sulfonation, and alkylation. You'll notice this is not a Friedel-Crafts alkylation because we aren't using the aluminum trichloride catalyst. Okay, so it's just a standard alkylation reaction or alkylating reagent. Okay. So there's our summary of all of our potential EAS reactions. So that's everything up in red. Okay, all of those have now been discussed and covered. When we move into the blue functionalities, these are pretty much reagents that are just told to you. We don't look at the mechanism for them at all. You're just kind of told this is what happens when you react it with that. The common cases of why, in most of these situations, they're almost all metal-involved reagents. As soon as we throw in metals, organic chemists tend to kind of gloss over and have no idea what the hell's going on anymore. And I am definitely no exception to that rule. Okay? So we throw in the metal, hey, it works, okay, let's just publish it. Okay? Now everybody can use it and move forward. So what we can go through and do is convert some of those functional groups over into other characteristics. For instance, if we start with the nitro, we can form our nitrobenzene and then convert it to an amine. Okay? Why would we convert to an amine? Well, with any of our other EAS reagents, could we put on an amine? No. So if I wanted an amine, I need to somehow make it from the other reagents. So that reagent, the iron or zinc, and I think technically tin as well as a possibility, with HCl will act as a reducing agent and turn the oxygens on our nitronium into hydrogens. Okay? Going to be in a really important reagent, actually, or sequence of steps, which we'll talk about when we look at activating versus deactivating. The one reaction which you should be familiar with is the excess NBS. Okay, NBS was what type of a reagent? When did you use that? Dealing with bromine, so if we look, yeah, we do have bromine on it. Radical substitutions. We're running a radical substitution where we're swapping out the hydrogens for a bromine. Okay, that carbon is resonance stabilized, okay, which you should be able to prove. So we can end up doing reacting that reagent with a lot of NBS, and we can do a substitution for each of those hydrogens for bromines. The next two, the next one is, again, kind of an odd situation. We can convert the CH3 directly across into a carboxylic acid by just oxidizing it. So we grab one of our strong oxidizing agents, which you should remember are permanganate, being a strong oxidizing reagent. That'll convert it across to the carboxylic acid. Okay? Also a very common one to show up. We'll talk about that one in a little bit more depth as well. The last one, you'll notice, is kind of similar to the very first one. What we're doing is removing oxygens. We're doing what type of a reaction? Reduction. We end up adding again our acid, our HCl, and then some kind of metal. Okay? So that can help us reduce that off. Why might we run that reaction? That's an interesting question. Okay? How else could we make that species? So we did a substitution for a carbon chain. What reagent could we use to get a carbon chain onto a ring? Acylation brings on the carbonyl, which is what we did here. I'm saying there's another way we could do it. Not acylation, but alkylation. We could have done a Friedel-Crafts alkylation. That's FC, by the way. I'm not trying to say it's a grade. Okay? We can do a Friedel-Crafts alkylation to put on that carbon. Okay, so that seems a bit odd. Why would we go through two steps when we could go through one instead? Turns out there's some complications with the alkylation reaction that we don't encounter with the acylation reaction. Okay? So, when trying to go through and do problems, be aware of these sneaky chemistries, the ones in blue. Okay? The ones in red, in theory, are straightforward. You should be able to nail those down pretty swiftly and quickly. Anything in blue is kind of a sneaky, tricky one. Watch out for that popping up. Good way to end the class and start the class. So here's the questions. We officially only have 3 minutes, so I'll let you take a look at these.